The universe is made out of dark matter. Dark matter surrounds the Milky Way galaxy. If it wasn't for dark matter, the Milky Way galaxy would have spun out of control and the Earth would be flung into outer space. And then here's the big question.
For years, astronomers and astrophysicists have been looking up, trying to understand what exists out there in the universe and figure out why it looks the way it does. When we use telescopes to gaze at the sky and collect as much light as we can, we find billions of galaxies. But these galaxies aren't just randomly distributed throughout the universe. They follow a structure that's driven by the force of gravity and guided by the presence of dark matter, a particle in the universe that has mass and doesn't give off or reflect light. And although dark matter makes up over 80% of all matter in the universe, scientists have never seen it. We only assume it exists because, without it, the behavior of stars, planets, and galaxies simply wouldn't make sense. Here is what we know about it, or rather what we think we know. But now, thanks to the ability to peer back to the dawn of the universe, the James Webb Space Telescope, or JWST, just detected the first ever evidence of dark matter, leaving scientists scratching their heads because this discovery has challenged all the scientific theories explaining the mystery of dark matter. Join us as we dig deep into the James Webb Space Telescope's new discovery, revealing the first ever evidence of dark matter that will quite simply blow your mind. A series of powerful observations has made it clear that our universe has expanded for billions of years, emerging from the hot, dense initial state we call the Big Bang. Over the past several decades, new types of precise measurements have allowed scientists to scrutinize and refine this account, letting them reconstruct the history of our universe in ever greater detail. When we compare the results from different kinds of measurements, the expansion rate of the universe, the temperature patterns in the light released when the first atoms formed, the abundances of various chemical elements, and the distribution of galaxies and other large-scale structures, we find stunning agreement. Each of these lines of evidence supports the conclusion that our universe expanded and evolved in just the way that the Big Bang theory predicts. From this perspective, our universe appears to be remarkably comprehensible. But cosmologists have struggled, if not outright failed, to understand essential facets of the universe. And dark matter is likely the most celebrated problem facing modern cosmologists today. The problem? It is completely invisible. It emits no light or energy and thus cannot be detected by conventional sensors or detectors. The key to its elusive nature must lie in its composition, scientists think. Visible matter, also called baryonic matter, consists of baryons, an overarching name for subatomic particles such as protons, neutrons, and electrons. However, astronomers have determined that most of the matter in our universe does not consist of atoms or any other known substances, but of something else, something that does not appreciably radiate, reflect, or absorb light: dark matter. Despite not knowing much about the nature of dark matter, cosmologists often speculate about the kinds of particles that might make up this substance. In particular, researchers have long recognized that if dark matter particles interact through a force that is approximately as powerful as the weak nuclear force, which governs radioactive decay, then the number of these particles that should have emerged from the Big Bang would roughly match the measured abundance of dark matter found in the universe today. With this in mind, weakly interacting massive particles, or WIMPs for short, became the best guess for dark matter's nature. And with this guess, scientists thought they knew how to detect these particles and study their properties. Motivated by this goal, physicists engaged in an ambitious experimental program to identify these WIMPs, weakly interacting massive particles, and learn how they were forged into the Big Bang. Over the past couple of decades, researchers have deployed a succession of increasingly sensitive dark matter detectors in deep underground laboratories that are capable of detecting individual collisions between a dark matter particle and the atoms that make up the target. These sophisticated experiments performed beautifully, as well as or better than designed actually, yet no such collisions have been observed to date. A decade ago, many scientists were optimistic that these experiments would bear fruit, but dark matter has turned out to be very different and far more elusive than we had once imagined. Although it's still possible that dark matter could exist in some form of difficult-to-detect WIMPs, the lack of any signal from underground experiments has led many physicists to shift their focus towards other dark matter candidates. One such contender is the hypothetical ultralight particle known as an axion. Axions are predicted according to a theory proposed by particle physicist Roberto Pecchiai and Helen Quinn in 1977. Although scientists are searching for axions in experiments that use powerful magnetic fields to convert them into photons, these investigations have yet to place very strict constraints on the properties of these particles. Another possibility that could explain why dark matter has been so difficult to detect is that the first moments of the universe may have played out much differently than cosmologists have long imagined. Take the case of the conventional WIMP, again weakly interacting massive particle. Calculations show that the fledgling universe should have produced vast quantities of these particles during the first millionth of a second or so after the Big Bang, when they reached a state of equilibrium with the surrounding plasma of quarks and gluons and other subatomic particles. The number of WIMPs that could have survived these conditions and ultimately contributed to the dark matter found throughout today's universe depends on how and how often they interacted. But when carrying out calculations such as these, scientists generally assume that space expanded steadily during the first fraction of a second, without any unexpected events or transitions. It is entirely plausible that this simply was not the case. Although cosmologists know a great deal about how our universe expanded and evolved over most of its history, they know relatively little about the first seconds that followed the Big Bang, and next to nothing about the first trillionth of a second. When it comes to how our universe may have evolved, or to the events that may have taken place during the earliest moments, we have essentially no direct observations on which to rely. This era is hidden from view, buried beneath impenetrable layers of energy, distance, and time. Our understanding of this period of cosmic history is, in many respects, little more than an informed guess based on inference and extrapolation. Look far enough back in time, and almost everything we know about our universe could have been different. Matter and energy existed in different forms than they do today, and they may have experienced forces that have not yet been discovered. Key events and transitions may have taken place that science has yet to illuminate. Matter likely interacted in ways that it no longer does, and space and time themselves may have behaved differently than they do in the world we know now. With this in mind, many cosmologists have begun to consider the possibility that our failure to detect the particles that make up dark matter might be telling us not only about the nature of dark matter itself, but also about the era in which it was created. By studying dark matter, we, as famous physicist Michio Kaku said, are learning about the first moments after the Big Bang, as well as conjecturing ultimate fate of the universe.
Until we solve the mystery of dark energy, we do not know the ultimate fate of the universe.
The Big Bang occurred 13.8 billion years ago. 1 second afterwards, the universe consisted of radiation, hydrogen, helium, and high-energy particles at a temperature of 18 billion degrees Fahrenheit. Around 400,000 years later, the temperature had cooled to 5,500 degrees Fahrenheit, and the universe was glowing dull red. As the universe continued to expand and cool, that glow disappeared, and the universe became completely dark, the so-called Dark Ages. The particles from the Big Bang grouped together due to gravity and formed the first atoms. These atoms grouped together in clumps, eventually becoming stars. When the first stars formed, they also began to emit the first light, which the time machine, the James Webb Space Telescope, was built to detect. The JWST has been designed to answer many of the core questions that have animated astronomers over the past half-century. With a $10 billion US price tag, it is one of the most ambitious engineering initiatives ever attempted, with the goal of nothing less than to rewrite the history of the cosmos and reshape humanity's position within it. Now, in another and a growing series of triumphs, the James Webb Space Telescope may have found evidence of a strange and elusive type of star that only existed in the very early universe, when invisible dark matter was one of the only available fuel sources. New research suggests that 3 of the earliest objects identified as galaxies by the JWST aren't galaxies at all, but rather dark stars, immense, ultra-bright hypothetical objects that are powered by dark matter rather than nuclear fusion. If the theory is correct, then this could finally help scientists better understand dark matter, the universe's most mysterious component. These things are atomic matter that is powered by dark matter, and one supermassive dark star could be as bright as an entire galaxy containing normal fusion-powered stars. Astrophysicist Catherine Fries, an astrophysicist at the University of Texas at Austin and lead author of a new study published July the 11th in the journal Proceedings of the National Academy of Sciences, said, "According to theory, dark stars are enormous in comparison to ordinary stars that exist in the universe today, like the Sun. Dark stars are hypothesized to have widths hundreds of times greater than that of the Sun. These stars, composed mostly of hydrogen and some helium, existed in proto-galaxies when the universe contained mostly those 2 elements, helium and hydrogen. Heavier elements hadn't yet been forged by nuclear fusion in stars. However, about 1/1000th of a dark star's mass would be made up of a secret fuel source, dark matter. Dark matter, which is all but invisible because it doesn't interact with light, makes up an estimated 85% of the matter in the universe. Theory suggests that when 2 dark matter particles collide, they may annihilate each other, turning their combined mass into a shower of energetic gamma-ray radiation. If dark matter is self-annihilating, then the annihilation products could get stuck inside this hydrogen cloud that makes up dark stars, Fries said. And what that means is you're taking all of the energy that used to be in the mass of the dark matter and dumping it into this cloud, Fries concluded. Fries also added that while everyday stars depend on high temperatures, dark matter annihilation could occur at any temperature. Dark matter annihilation doesn't care about the temperature, she said, so you have dark matter annihilation throughout the entire width of the dark star, and the surface temperature is relatively cool. Because of that, there's no ionizing photons or other stuff coming off, preventing the accretion of more matter. In contrast, when normal stars have acquired enough mass to start nuclear fusion, the radiation that they pump out pushes away the gas envelope that surrounds them, preventing them from accreting more matter and thus growing further. This means that, while dark stars may start out with a mass about the same as the Sun, the objects can accrete more and more matter, growing to be 1,000,000 times as massive as the Sun, and 1 billion times as bright, Fries added. Given their huge size, dark stars would appear as more spread out objects rather than as point-like objects, like modern-day stars. This is how three ancient objects were detected by JWST, named JADES GS Z13-0, JADES GS Z12-0, and JADES GS Z11-0. These could have been misidentified as galaxies, according to the new research. And excitingly, these candidate dark stars date to between 320 and 420 million years after the Big Bang. But the dark matter annihilation process can't continue forever. Dark stars sit in the dark matter-rich centers of protogalaxies, which merge together continuously to form proper galaxies, and eventually this moves dark stars away from their dark matter fuel. As dark stars get displaced from the dark matter-rich center, the dark stars start collapsing, Friis explained. This will trigger fusion in the smaller ones, creating ordinary fusion power stars, which are all created from collapsing clouds of gas. The bigger ones will collapse immediately into black holes, she said. This means that dark stars don't exist in the universe today, Friis summarized. However, it's difficult to pinpoint exactly when, in the 13.8 billion year history of the universe, that dark stars would have ceased to be. Confirming the existence of dark stars via these JWST observations would be huge, but Friis pointed out that she and her team aren't quite there yet. This confirmation would require either looking at these candidate dark stars for much longer to build a more complete picture of their light output, or waiting for magnified observations that better reveal the light emissions of these objects, which could allow scientists to identify whether the objects have pure hydrogen or helium compositions, as would be expected from dark stars. The dark star idea has been hanging in there for many years, and it would be extremely exciting to me to have this proven correct, Friis concluded. While the first ever evidence of dark matter appears, scientists expect that the James Webb Space Telescope will continue to promote its outstanding power, not only unlocking the mysteries of dark matter, but also dark energy. Because, after all, dark energy is even more mysterious than dark matter. Even its discovery itself in the 1990s was a complete shock to scientists. Previously, physicists had assumed that the attractive force of gravity would slow down the expansion of the universe over time. But when two independent teams tried to measure the rate of deceleration, they found that the expansion was actually speeding up. One scientist likened the finding to throwing a set of keys up in the air expecting them to fall back down to Earth, only to see them fly straight up towards the ceiling. Scientists now think that the accelerated expansion of the universe is driven by a kind of repulsive force generated by quantum fluctuations in otherwise empty space. What's more, the force seems to be growing stronger as the universe expands. For lack of a better name, scientists call this mysterious force dark energy. Unlike dark matter, scientists have no plausible explanation for dark energy. According to one idea, dark energy is a fifth and previously unknown type of fundamental force called quintessence, which fills the universe like a fluid. Many scientists have also pointed out that the known properties of dark energy are consistent with a cosmological constant, a mathematical band-aid, if you will, that Albert Einstein added to his theory of general relativity to make his equations fit with the notion of a static universe. According to Einstein, the constant would be a repulsive force that counteracts gravity, keeping the universe from collapsing in on itself. It's interesting to note that Einstein later discarded this idea when astronomical observations revealed that the universe was expanding, calling the cosmological constant his biggest blunder. Now that we see the expansion of the universe is accelerating, adding in dark energy as a cosmological constant could neatly explain how space-time is being stretched apart. But that explanation still leaves scientists clueless as to why the strange forces exist in the first place. After all, having admitted that everything we know, everything we can see, is just 5% of everything in the universe. The remaining 95% of the universe is stuff that we can't see, or in other words, what we don't yet understand. And so, an extraordinarily vast portion of the cosmos is still unknown, and despite the technological advancements of the last century, even with the computers at our very fingertips, and the worldwide internet and space-based observatories mapping the far reaches of our universe, there is still so much more that we don't understand. We have grown in leaps and bounds since the days of the ancient Greeks and Egyptians, ever since Copernicus and Kepler, but in many ways, we are still novices playing with toy models, seeking to understand the magnificent stars. At the end of the day, we are simply on a lone planet, dangling in space, orbiting a sun amidst millions of other stars, in a small corner of a remote galaxy in an ever-expanding universe. However, it is in our nature as humans to seek meaning in the stars, but sometimes the answers aren't the ones we are searching for. Well, that's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit that bell so you never miss out on future episodes. And be sure to tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content like this and to always improve. As always, thanks for watching, and we'll see you next time.